Now, before we go too far into this, I want to bring our memory back to the first time we did a projectile motion, maybe. Was it here? Maybe not. Maybe it was here. There's our pretty picture. Oh, this picture was so nice. Do you guys remember this picture we drew? Yeah, it was so pretty. There was a lot of stuff going on. Do you remember we had this ball C, that was just rolling across the way? Remember that? And it had a constant velocity. Doop-a-doop-a-doop-a-doop-a-doop. Then you had this ball that was falling, ball A. This is the one from the demo. And what happened to the velocity of this ball as it fell? Do you remember? It got faster and faster and faster in the negative direction. Remember that? And then we smashed them together into one object that was moving with a horizontal velocity initially, and it kept going in the horizontal velocities. Remember, those blue lines were all constant. Does that sound familiar to you? But then the purple lines got longer and longer and longer because it kept going faster and faster and faster. I'm going to take this concept now, and instead of launching it from the very top, I want to launch it from down here. Okay? I'm not going to try and draw right on top of this picture because that would get really confusing super fast. So I'm going to draw it separately, but I want you to keep that in the back of your mind. Remember that picture. So here we go. Oops. There we go. So you're going to draw a picture. We're going to draw some grass. We're going to think back a couple weeks to launching our little projectile, our little rockets. Remember that? It was so nice outside. In the other class, one of my kids who wasn't there on the launching day was like, wait, if we're doing it now, how come we didn't launch rockets now? I'm like, well, because there's like the potential for there to be snow on the ground today, right? So I didn't want to risk it. It was a beautiful day. So here we go. Now what I want you to do is I want you to draw the trajectory of the rocket. Where's it going to go? Or where did it go if you saw it? Or if you were watching Sam throw that frog, where did that go? What is that trajectory going to look like? There's a mathematical term that describes it. You want to throw it out there? It starts with a P. It is a parabola. It is a parabola. It's going to go up, 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 and down, 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 down. Something like that. Okay. I'm going to zoom in because I like to do that. Now, usually I would draw rockets each time, but that seems like a lot of work. So instead, I'm just going to draw dots. So I'm going to draw a few dots here. 1, 2, 3. One at the very top. 1, 2, 3, 4. So far, so good? This has some initial velocity in the x. Do you agree? Okay. We could oh man, this will be so fun. Are you ready for this? I'm going to draw that initial velocity vector. It looks like this. It's going in that direction. We could even, because we're not magical, we've just listened and we know how to do physics. We could even acknowledge that there's some in the x direction and some in the y direction. Are you with me there? Hey, we just did this yesterday, Miss K. I know we did, right? The initial velocity, there's some in the x direction. Tell me about the velocity here in the x direction. How does it compare to this? Assuming there's no air. The velocity in the x direction speeds up, slows down, or stays the same? Just in the x direction. Megan was talking with her hand over her mouth like this. I don't know what she said for sure. What did you say?
It stays the same.
Why do you think it stays the same? Because it does. Because it starts with an A. It's not what? It's not accelerating. Next chapter, we're going to talk about what causes that acceleration, but there's nothing pushing or pulling on it, right? It doesn't have a little rocket pack on it that after it's launched, it keeps going, and it doesn't have any friction that's slowing it down. So in the x direction, high five to Miss Megan, yeah, boom, it does not change. So it's going to stay the same. It's going to stay the same the whole way across. So go ahead and draw those x velocity arrows. They're the same all the way. I hope mine don't look like they're getting bigger. I don't intend for them to. I'll slow that down a little bit. In the x direction, the velocity is the same the whole darn time. Those don't look exactly perfect, but you know, be nice to me. Okay. I wish I had like a big thing that I could just like cover up this half. Have you seen a trajectory that looks like this before? Like in that page that I showed you before? From the top down, what's the initial velocity in the y, or the velocity here in the y direction? At the very top. What is it? It's 0. It's only moving. If you look at this line compared to the trajectory, it's only moving in that direction. Are you with me there? Is that okay? What about here? Is it moving down a little bit now? And what about here? How does the speed compare from the top down, 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 down? What do you think? Speeds up, slows down, stays the same. What is it? Speeds up in the negative direction, right? It speeds up in the negative direction. So there's a 0 at the top, and then a little bit later it's like this, and a little bit later it's like this, and a little bit later it's like this, and a little bit later it's like this, yeah? Why is this true? It's that A word again. What was it? It's accelerating. Yeah. So the velocity in the y direction changes because the object, is accelerating. Okay. What do you think it's doing here? Here to here to here. Speeding up or slowing down? Slowing down. How would I represent that on my picture? That's the velocity I got to start. What's going to happen here? Same? Smaller? Smaller? Itty bitty? 0. Yeah. Smaller, smaller, itty bitty 0. We doing okay? So at any given point, except for the top, you've got some in the x and some in the y. It's all right. But again, just like we said before, the motion in the x does not affect the motion in the y. Vx does not change. That's the concept behind it. Let's write out some givens, some things that we know. We're going to solve these problems exactly the same way that we did before. By that I mean we're going to use the exact same chart that we used before. dx, vx, ax, dy, vy, ay, and it's all tied together by time. What are the things that we know on this chart always and forever? Acceleration for what? Did you say Vy? Is what? Indeed. How about in the x? 0. The dx is something we're usually going to look for. In our other problems, Vy, or the initial velocity in the y direction, was 0. Is that true now? It's not true. We got to figure it out. Let's write out how we're going to do it. This is the initial velocity. I've got an X piece and I've got a Y piece. And guess what they're also going to tell me? An angle. Hey, did you learn how to do this already? Can you figure out if I tell you that it was launched at 3.3 meters per second at an angle of 22 degrees above the horizontal? Can you figure out what the initial velocity in the Y was, and the initial velocity in the X is? For sure you can. Vx is like the adjacent side of the triangle, right? So we could do this. Let's write it out so we've got it. So we can say that the cosine of theta is equal to the initial velocity divided by the velocity in the X. So we could say, oops, I wrote that backwards, sorry. Vx and Vi, I apologize for that. Vx is equal to cosine, oops, oh my gosh, getting ahead of myself. You can do the same thing in the Y. And we can use those two things in our chart to solve for stuff. I'm going to give you a problem to draw a picture for and fill out givens for. Does that sound reasonable? Okay. This is one that happens to be in your book, so you don't need to copy it down for sure. It's page 101, number 1. You're going to do 2 and 3 for homework today. So this says, blah, 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 fleas jump, blah, blah, blah. Okay. The flea's initial speed is 2.2 meters per second, and it leaps at an angle of 21 degrees with respect to the horizontal. Oh, it tells us the time. The jump lasts 0.16 seconds, and it says, what is the magnitude of the horizontal displacement? And then it asks us something more interesting, too. How high does it go? Okay. So you should draw a picture. Write down as much of your givens chart as you can. It's really okay to talk out loud, you guys. You do not need to whisper. You really don't need to. Tell me if I've made a silly mistake, though, please. Are you getting the same numbers that I got? Or no? Okay, good. Please let me know if I don't. To make sure this is making sense to you. So our initial instinct is to say, okay, well, I need to find dy, right? Because it says how high does it go? Well, that's a dy question. So I need to figure out, well, I'm just going to use the dy stuff. But here's the thing, ladies and gentlemen, this is the kicker. This is why every problem is not exactly the same. It's not formulaic. You have to use your brain. You have to process. Darn it. Okay. What does this time represent? What does this time represent in the y direction? Where's the flea go? Where does he go? Talk to me about his y displacement. Nowhere. He goes nowhere. So you got 0, didn't you, Madeline? Is that what you were? Yeah. Because so what you did was right, it just didn't answer the right question. So Madeline was getting mad at me. I'm gonna totally just like throw that out there. She put in time as 0.16 and AY and VY just like we've done before. And when she got DY, she got essentially 0. Which is correct, that makes sense. But that's not the maximum height, is it? We have to be a little bit clever to figure out the maximum height because we want to know what the time is or what the height is, what dy is when the flea is up here. Divide what by 2? Yeah. Takes the same amount of time to go up as it does to come down. So it takes 0.16 seconds to go up and down. Divide that by 2. That'll be the time to go up, and that'll tell you the dy you actually want to know. So that would be like a separate question, right? There you go. Friendly reminder, though, that you're going to work on numbers 2 and 3 on the same section for tomorrow. Have a fantastic day. Get some rest this evening, friends.